Now in this example we have a system 3 by 3 to solve. Now again we call the three equations, for example E1, E2 and E3. Now as you can see in the third equation I already have x that can be written in terms of z only, so x is 5 minus 2z, so basically we're using the substitution method here. So for E1 I replace x by its expression. So first multiply x by 2, I get with 10 minus 4z minus y plus 5z equals to 4. Then simplifying this, we end up with negative y plus z equals to negative 6. And doing the same thing with E3, with, with E2. Then replacing x by 5 minus 2z plus y plus z equals to negative 4, I end up with y minus z equals to negative 9. So we obtain this 2 by 2 system, which consists of these two equations we obtained here. Now you notice here that by adding these two equations, negative y plus y and z minus z are both zeros, equals to negative 15 on the second side. Now we ended up with a false statement. 0 is not equal to negative 15. That's impossible. So for this reason, the solution set of the system is empty. It's phi. The system has no solution. So whenever the 2 by 2 system you obtained ended up giving you a false statement, in that case the system would basically have no solution. Now, if we move to this example here, similarly, we can start by naming the equations E1, E2, and E3, and we can use the first equation to write x in terms of y and z as x equals to 4 minus y minus z. Then, when I replace in E2 the expression for x, I end up with 4 minus y minus z minus 2y plus z equals to 4. So you notice that the terms in z cancels out and we end up with negative 3y equals to 0, then y is 0. So over here, since we already got a value for y, we can basically replace it in E1 and E2 and reduce the system for a 2 by 2 system in x and z. So by replacing y by 0 in E1 and E3, we get x plus z equals to 4 and 3x plus 3z equals to 12. Now, you notice that over here, when you solve the system, when you do it by elimination or by substitution, now the second equation can basically be divided by 3, or the first equation can be multiplied by 3. We end up with a system containing the same equation. So over here, by solving the system, by subtracting the first and the second equation, we end up with 0 equals to 0. Now the 2 by 2 system we ended up here did not lead to a false statement. It led to a true statement. This is true for all x and z. So basically over here in this case, the system has infinite number of solutions. But of course, infinite number of solutions does not really mean that any value of x, y, and z would basically satisfy the system. So over here, the infinite number of solutions are basically following a certain pattern that we need to determine. Now, if we go back to the 2 by 2 system that was consisting of the same equation, x plus plus z equals to 4. So in order to determine the pattern among the values of the triplets forming the solution set, which is infinite of the system, basically we start by setting one of the variables as a solution. We have x and z in this equation, so we start by taking z equals to m. So we consider one of the variables as a parameter. Over here we considered z as m. So we go back to that equation, x plus z equals to 4, then x would be 4 minus m. Now over here we have z and x both written in terms of the parameter. Now since we already have y equals to 0, then fine, we're done. But if we did not have y equals to 0, then we would have to go back to the original system and find y in terms of m as well. So over here, the system, the solution set of the system would basically consist of the triplets in the form 4 minus m, 0 for y, and m for z, where m is a real parameter. Okay, so what does this basically really mean? It means that the solutions of the systems, the triplets x, y, and z that basically satisfy the system are all in this form for any value of m, which means, and since m can take infinite number of values, in that case we can have infinite number of triplets all fitting into this pattern. For example, for m equals to 0, we end up with the triplet 4, 0, 0. And by replacing 4, 0, and 0 for x, y, and z in the system, you would see it would satisfy the system. For example, for m equals to 1, when m is 1, we would have the triplet 3, 0, 1 as a solution. For m equals to -1, we would have the triplet positive 5, 0, -1 as a solution. For m equals to half, we would have the triplet 7 over 2, 0, half as a solution, etc. And this can keep on going infinitely, since m can take any real number as a value. So infinite number of solutions does not mean that any triplet x, y, and z satisfies the system. The infinite number of triplets that satisfy the system are in the form 4 minus m, 0, m, where m is a real number. So whenever you end up with a system that has infinite number of solutions, you have to basically write the solution set in terms of the parameter that determines basically the patterns the solutions of the system follow. Now, over here, this example is basically a bit different than the other examples we solved so far. The other examples consisted of systems 3 by 3 that we needed to solve. Now, over here, as you can see that this system involves a parameter. It already has an unknown coefficient here. So the question asks us to discuss the solution of the system below with respect to the real parameter a. So we need to discuss, depending on the different values of a, the solutions of the system. So basically we can start by solving the system similarly to what we've done already, using any of the three methods that we took. So we could, basically, since we've been using substitution up to this point, we can keep on doing so. Now over here for the second one, we can basically write x as 1 minus y minus z. So over here I replace x by that expression in E1 and E3. So for E1, we would basically have a into 1 minus y minus z plus y plus z equals to 3. When we fix this as a term in y plus a term in z equals to a constant, we basically end up with 1 minus a into y, when we expand the first term, of course, and group similar terms, and 1 minus a into z equals to 3 minus a. Now, as for E3, when I replace x by its expression in E3, I end up with 1 minus y minus z plus 2y minus z equals to 2. Then it's y minus 2z equals to 1. So now we end up with this system 2 by 2 in y and z involving the parameter. So if we open up a new page here, we write the system. We have y minus 2z equals to 1. And we have 1 minus a into y plus 1 minus a into z equals to 3 minus a. Now we could use elimination for this, and we could multiply the first equation by a minus 1, since a minus 1 is the opposite of 1 minus a. So this leads me to the system a minus 1 into y minus 2 into a minus 1 into z equals to a minus 1, and of course the second equation here. Now by adding these two equations, the terms in y, since they have opposite coefficients, they cancel out. Now as for the factors of z, we have negative 2a plus 2 from the first equation plus 1 minus a from the second one equals 2. Now, as you can see on the other side, the a's cancel out, which does not always happen, by the way. But over here, it happened that the terms in a canceled out and we ended up with a 2. So by simplifying here, we end up with 3 minus 3a into z equals to 2. So this is where we basically start our discussion. We start solving the system until we get to an equation with one variable involving the parameter, of course. So this is where we start our discussion. Now, what does basically make a 3 by 3 system having no solution or an infinite number of solutions or a unique solution? Now, if we go through the different cases here, if we open up the small box here, now the system would basically have a unique solution, exactly one solution, when we can get a value for x, a value for y, and a value for z, which, for example, when we start solving the system, when we end up with a system with an equation with one variable in the form, for example, 3z equals to 2. Now over here I'm able to determine a value for z because the coefficient of z here was different than 0. So when the coefficient of z here is different than 0, I'm able to find z, and consequently I'm able to find a value for y and a value for x. So therefore, when the coefficient of the variable is different than 0, in that case we end up with a unique solution. On the other hand, we end up with infinite number of solutions or no solutions when the variable cancels out, which means that when we end up with 0 equal to any value different than 0, where m is not 0, or when we end up with 0 equals to 0. So when we end up with a 0 equal to a value different than 0, in that case the system has no solutions. And when we end up with 0 equal to 0, the system would have infinite solutions. So over here, if we go back to our equation, since I have over here the other side, the right hand side is already different than 0, then in this case this possibility cannot happen. There's no value for a which would make this equation be in the form 0 equals to 0. So this possibility is ruled out. So we're left with these two possibilities. Since the other side is already different than 0, then the solutions of the system depend on the first side, the coefficient of the variable z. If the coefficient of the variable z is equals to 0, in this case we would basically have 0 equals to 2, which that would be no solution. If this is different than 0, in that case, I'm able to find z, and the system would have a unique solution. So over here, it all depends on whether the coefficient of the variable is 0 or not. So 3 minus 3a is 0 when a is 1. So these are my cases. So for case 1, if a is equals to 1, in that case, the equation is reduced to 0 equals to 2, then the system wouldn't have any solution. Now, if a is different than 1, in this case, the system would have or admits a unique solution, which our equation would basically give us z equals to 2 to 3 into 1 minus a. Now I go back to my equations to find y, as I already found z in terms of the parameter. So over here, according to this equation, y is, sorry about that, so it's 1 plus 2z, which is 1 plus 2 over 3 into 1 minus a. So by reducing to the same denominator and simplifying, that would be 5 minus 3a over 3 into 1 minus a. And then I go back to this equation here in terms of, for x in terms of y and z, which is x equals to 1 minus y minus z. So it's 1 minus 5 minus 3a over 3 into 1 minus a minus 2 over 3 into 1 minus a. So over here, I reduce to the same denominator, opening a new page here. So x would basically be some fraction with 3 into 1 minus a at the denominator. The first term being 1, so I multiply it by the denominator. Now, the other two fractions already have that common denominator, so I just expand the minuses into them. Don't forget, whenever we have a negative in front of a fraction or multiplying a fraction, the negative either multiplies the whole numerator or the whole denominator. So over here we're going to expand it into the numerator, so that's negative 5. So that's negative 5 plus 3a, and then minus 2. Okay, so simplifying this, we get negative 3a plus 3a, that's a 0, so the a cancels out, and that's a negative 7 plus 3a, so that's a negative 4. So that's a negative 4 over 3 into 1 minus a. So over here, do not forget that we're still working in the case where a is different than 1, where the system has no solution. So in this case, the solution set of the system would be x, which is negative 4 over 3 into 1 minus a, and y, which is 5 minus 3a over 3 into 1 minus a, and finally z, which is 2 over 3 into 1 minus a. Now, so this is the triplet x, y, z, but do not forget that this is in the case where a is different than 1, because when A is equals to 1, the solution set is just empty. There would be no solution. So when A is different than 1, the solution set of the system is basically unique, and it would be in this form according to each value of A.